Well, hello everyone. My name is Martín, and I'm working in the EAP lab under the supervision of Marco Rayola and Carlos San Miguel Vila. And today I'm going to present you my work in this year, which in principle is under the thesis title Closed-Loop Jet Control for Aeronautical Applications. But in reality today, we are not going to discuss this, and something more appropriate would be a title like A Year into Pattern Recognition Techniques and Reinforcement Learning. Let's start first with a little bit of motivation, because we want to control jets, as Luca explained earlier, because they are everywhere pretty much in aerospace applications. From free jets appearing at the exhaust nozzle of turbojet and turbofan engines, to impinging jets used within turbine blades in order to cool them up. They are a really cool technology that enable the core technology for aircraft and rocket engines. They allow for advanced cooling technology, and in principle, they would allow for flow manipulation and aerodynamics control. But there are some cons associated with them that hinder their applicability in reality. For instance, they introduce acoustic pollution, mainly through jet noise, which is key for the noise that these engines emit to the atmosphere. Efficiency losses due to uncontrolled turbulence in these engines, and the chaotic behavior that these kind of jets present difficult the predictable implementation of jets in most practical industrial applications. So this has not been left untouched. Some people have been trying to control jets in different ways. We have, well, let's start talking first about jets in general, because this is the general structure a jet has, and there are some key parameters and key properties that we would like to discuss. For example, that they are advection dominated, so there is a delay between when we do something, if we do something, for example, close to the nozzle, and when we would sense it, that we will sense it downstream, as convection dominates these kind of flows. These jets have an initial region where the flow is amplifying any perturbation that you introduce to it, and later on turbulence starts growing and dominates the flow through dissipation, which limits where we would want to sense and actuate on these kind of flows. And finally, jets are broadband and chaotic, which increase a lot the complexity of any kind of algorithms that we want to implement for controlling jets. And indeed, as I was mentioning, there are different technologies that have been tried to be used to control jets. The most typical example, the chevrons at the exit nozzle of turbofan engines to reduce noise, as passive technologies where no energy is being input into the system. But there are different active technologies that use plasma actuator or synthetic jets to control different parameters of jets. And most importantly, and most recently, we have AI techniques to control jets, in this case with the objective of maximizing mixing at the exhaust of a jet. And recently, closed-loop control has been achieved for, again, the same purpose of maximizing mixing downstream from the jet, which is a really cool application. But we want to expand on this. And the question that we want to solve is if we can leverage data-driven techniques for allowing closed-loop control for more complex objectives, like, for example, noise reduction or enhancing heat transfer. The problem is really complex, and we want to leverage two different things in order to achieve this. First, the recurrent behaviors that appear in jets, because jets are chaotic, but there are certain patterns that appear over time. And maybe we can identify these patterns and target them. Also, reinforcement learning is like a data-driven approach to optimal control, and it has been applied for different kind of flows with a certain degree of success. So maybe we can try to implement this kind of framework for jets. There are a lot of difficulties to be overcome, but it shows potential for a purpose. So for doing this, let's try to organize our ideas and structure the problems. First of all, we would like to identify these recurrent structures, the first problem that we have to tackle. And indeed, what we want to do is to apply SPOD, a really powerful tool for extracting spatio-temporal patterns from a certain data set. The problem with SPOD is that you need time-resolved data. And as Luca discussed, it's not that easy to obtain experimentally time-resolved data. So what we thought is that maybe we can implement a different sampling strategy with, which is a discontinuous sampling, and modify the current SPOD algorithm to try to do something similar to SPOD, but from non-time-resolved data. We achieved positive results doing so in a synthetic database. And now what we want to do is to apply this same methodology into experimental data to check the statistical property that this methodology shows, to enhance the computational speed, because right now it's pretty low. And we would like to finally deliver an open source MATLAB implementation of this algorithm. Next, once we have identified our recurrent structures, we would like to relate these structures to the impact to the control objective. This block started with a slightly different question. And the thing is that we identify that pressure is quadratically related with flow velocity. So we wanted to think how different patterns in the flow relate to fluctuations in the pressure. We thought of a way of doing so, and indeed we were able to identify different pressure structures related to different flow conditions. We applied the algorithm into a flapping wing, so it's not exactly a jet, but in principle the framework can be implemented in any kind of flow database. And we achieved a statistical framework that was capable of identifying the most relevant flow structures for force fluctuations, which is great, but we are really interested in the inverse problem. Can we, from some sparse pressure acoustic measurements, identify the flow state? As you can guess, this is particularly interesting because we can, from measurements of microphones, infer how is the flow. Interesting for noise control reduction. And finally, once we have identified structures and we know how they impact our control objective, we want to train a reinforcement learning agent for this. And we are in the early stages for this part, but we have identified a key challenge, that is that reinforcement learning assumes that the Markovian property is fulfilled. That is a property that in general doesn't apply or doesn't fulfill in general control flow setups. So can we overcome this incompatibility to apply reinforcement learning into jet flows? For answering this question, we have built a stochastic environment that tries to simulate the kind of instabilities that we will watch and observe in a jet. We have applied reinforcement learning in the ideal case with all the necessary information, and indeed we have achieved control. And when we tried to break this property, this Markovian property, we have indeed shown that control fails. Now what we want to do is to take advantage of Taken's embedding theorem to recover the Markovian property. This is pretty much everything, but this is not all that we want to do because there are some missing links. For example, how can we go from flow inference framework to how can we apply this framework for spatiotemporal structures? Or how can we use these recurrent structures to define a reward and a state for the reinforcement learning algorithm, which is not a trivial technique. That's pretty much everything that I want to discuss today. These are some of the achievements that I've been doing this year with some diverse stuff. And that's pretty much everything. Thank you very much. If you have any questions, I will get to answer them.